Hello guys, welcome to this YouTube channel. In this video we are going to solve the question I have on the board here, and it's a question under fluid kinematics, which simply means fluids in motion. And here the question states that we are to determine if there are any stagnation points in this fluid flow or in this flow field, and if so, where are they? So at the first place we have to read the question above, and also they've given us some conditions. That's three conditions: a steady state condition, an incompressible state condition, and also a two-dimensional flow. So we have the steady states, we have the incompressible, and also two-dimensional, which would give us a clue on how to solve our question. So for a steady state simply means a constant time. So it's in the function of time. And for the incompressibility or the incompressible flow, it's in the function of density. And for this, it's a 2D model. So it means if you look at the next line, that's the equation given, you can see that the u and v represents the x and the y axis. It means the z axis or the z axis is going to be equal to 0. So we are just going to make use of the x and y axis as is stated here. So for the first question, in order to help us solve, we have to understand what stagnation means. For stagnation, it means in simple terms, it means the velocity at that point is equal to 0. So we are going to make the velocity at this point equal to 0. And if there are some particles at that velocity, it means there is stagnation. That's in simple terms. So let's go ahead and solve the first one. That's A. So the first one, making the velocity vector equal to 0. That means your u side is supposed to be equal to 0. This is your u side, and this is your v side. It's also supposed to equal to 0. So let's start with the u side. So u is equal to 1 plus 3x plus y. So because we are finding for stagnation, we have to make u equal to, u is supposed to be equal to 0. So we are going to get 0 equal to 1 plus 3x plus y. So we can't solve this because we have two unknown and one equation, right? So we are supposed to find for the next one too. So we can name this as our equation 1. And for our second one, that's v is equal to minus 1 minus 2x minus 3y. So we set v is also equal to 0. So making it 0 equal to minus 1 minus 2x minus 3y. This is our equation 2. We can further simplify this into minus 1 equal to 3x plus y. So this is equation 1, and this is going to give us minus 1 equal to minus 2x plus 3y, equation 2. So we solve these two equations simultaneously. We are going to get our x to be equal to minus 2 over 7, and also our y to be equal to minus 1 over 7. So in getting this, we can write them in a point form. That's x comma y is equal to minus 2 over 7 minus 1 over 7. So this are stagnation points. So this shows that there is stagnation. There is some points in the fluid where the fluid particle is stagnant. This shows that there is some points in the fluid where the fluid is stagnant. So let's move on to the next one, which is our material acceleration. And for our material acceleration, we are supposed to find the material acceleration at some point, that's at x equals 2 meters and also at y equal to 3 meters. There is it. And we would have to resolve them in components from that in the x direction, also in the y direction, but because it's a two-dimensional, we are not going to resolve it in the z direction, but just our x and y direction. So it has made our work simpler. So we know for the b part, we know our material acceleration in the x direction is going to be equal to du dt plus u du dt, dx plus v du dy plus w du dz. So in this, at this point, so we have to make reference to the conditions which were stated in the question. That's a steady state, compressible, and also two-dimensional flow. So for a steady state, we know that for a steady state, the change in t is going to be equal to 0 because it's constant time. Let's say maybe the time interval is 1 second, 1 second. If you find a change in it, it's going to give us 0, right? So this whole thing goes to 0. So anything with time goes to 0. So this has been cancelled out. We also know that incompressible, right? So incompressible, we look for the densities, but there are no densities here. They are all in velocities. They are all in velocity form. They are all in the acceleration form, sorry. And then we move on to the next one, which is two-dimensional flow. And the two-dimensional flow, we were told that it's in the u and the v direction, or it's in the x and the y direction. So for the x and y direction, it means we are going to make use of this 2, meaning this is going to be equal to 0. So this makes our equation or our finding simple. So we are going to get ax is equal to u du dx plus v du dy. So we are going to find this. We know our u, we know this is our u, and we know this is our v. So we are going to differentiate them with respect to whatever we have here. So for our ax, we are going to differentiate. Let's find du dx. So we are going to differentiate u with respect to x. So there is the equation here. We are going to differentiate with respect to x. So if we differentiate this with respect to x, we are going to get our du dx to be equal to 3, and our du dy, if we differentiate this, the same thing, with respect to y, we are going to get 1. So we are just going to put them into this formula that we have, or this equation that we have here. So we know our u to be equal to 1 plus 3x plus y multiplied by the 3 we have here plus the v component, that's minus 1 minus 2x minus 3y multiplied by 1. So it can just multiply it by 1 here. And we were given x to be what? 2 meters and y to be what? 3 meters. So we can just put them into this equation we have here. That's 1 plus 3 multiplied by 2 plus 3, all multiplied by 3, plus minus 1 minus 2 multiplied by 2 minus 3 multiplied by 3, all multiplied by 1. So if you do your computation, we are going to get the material acceleration in the x, or the material acceleration at the x direction to be equal to 16 if you do the computation. So let's move on to the material acceleration in the y direction. So the material acceleration in the y direction, we are going to make use of v. For the x, we made use of what? The u. So for here, we are just going to change this into v, the differentials into v, which makes it simple for us. So we are still going to make use of this formula we have here. So this is ay. So ay is equal to u dv dx plus v dv dy. So now let's differentiate v with respect to x. So differentiating v, with respect to x, we are going to get minus 2, and differentiating v with respect to y, we are going to get negative 3. So let's put that into this equation and find for our ay. So we are going to get the same equation, 3x plus y multiplied by, what's our dv dx? That's negative 2, plus the whole equation, minus 1 minus 2x minus 3y, all multiplied by minus 3. So you putting your point into this formula, that's 1 plus 3 multiplied by 2 plus 3, all multiplied by negative 2, plus 1 minus 1 minus 2 multiplied by 2 minus 3 multiplied by 3, all of them multiplied by minus 3. We are going to get our ay to be equal to 22. We are going to get our ay to be equal to 22. So we have our ax to be 16 and our ay to be 22. So it means we calculating for the material acceleration at both points, or at the x and the y points, we are going to get the points to be, you can write ax comma ay to be equal to 16, 22. So that's the answer for the second one. So now we move on to the third one, which we've been asked to sketch velocity vectors at sample locations in the upper right quadrant. So our upper right quadrants are the positive quadrants. So if you take your Cartesian plane, you are going to have your points being drawn at this side, because this side is positive, positive, this side is negative and negative. So we can't draw it here because they said upper right quadrant. We are making reference to this, and they've given us the range of values we are supposed to use, and this range actually fits our work in the sense that there are no negatives. So maybe in case you see a question of this sort in your exams and they give you a range of -2 to, let's say, 4, and they give you, that's for the x, and they give you the same thing for the y, you don't have to start from the negative. You have to remember that they've made reference to the upper right quadrant, so you have to use the positive values, not the negative values. If you use the negative values, you've actually deviated from this. So let's go ahead and try and solve the C parts quickly. So for the C parts, we are just supposed to generate some sample points quickly. So the points you are supposed to generate, if it's an assignment base, you can generate about 30 points and over, or you can generate it with Excel, using Excel if you are very good at Excel. But if it's for exam sake, because you can't generate a lot of points, actually you can get more than 1 million points in just this range, but because we are bounded by time, we can't do all those here, so we have to just take some small points and get our job done. So if it's exam purpose, I think about 10 points is okay, or 7 to 10 points are okay. But if for assignment purposes, you can generate about 30 points because you have a lot of time. Yeah. So this is going to be our x, this is going to be our y, this is going to be our u, this is going to be our v. Then we have our magnitude, which is the square root, which is the sum of the squares of the u and the v, all of them square rooted. Then we have our angle, which is tan inverse of v over u. So these are what we are supposed to find for. So now you getting your points, you can decide to start from anywhere, any positive number within this range. So someone can start with 0.1 with an interval of 0.1, so maybe 0.1, 0.2, 0.3, 0.4. It's still a positive number. Someone can also start with whole numbers, so 1, 2, 3, depending on how fast you will be, if in case it's an exam question. So I'll start with 1, 2, 3, and maybe come back to 1, 2, 3, then 1, 2, 3. So let's get about 9 points. Then you come here to the same range. I can do that as no, let's clean this. 1, 1, 1, so 2, 2, 2, then 3, 3, 3. Yeah, this will be easier. Then you come to this side, 1, 2, 3, 1, 2, 3, 1, 2, 3. They are all random points you are generating, so someone can start with 2, 3, 4. Bearing in mind that the range is very important to us. So after getting this, you know your u is this. So wherever you see x, you are going to put 1 for the first side. Wherever you see y, you are going to put 1 for the first side and you put it here. Wherever you see, you come to the v side, to wherever you see x, you are going to put 1. Wherever you see y, you are going to put 1 for the first side. So let's tackle the first box. Let's tackle the u side. So we have 1 here, 1 here, which is going to give us 5. Yeah. So if you put 1 in this, you put the same 1 here, it's going to give us a sum of 5. So that's our u. Then for our v, we are going to put 1 here, which is going to give us -3 minus 3. That's going to give us -6. Then you find the magnitude. This is the magnitude for it. You find the magnitude. You are going to get So I'm going to get the square root of 61. The square root of 61. Then you find the inverse of that, so you are going to get something about 50.1 or so. So you do that for the rest of the points. Okay, so after the computation or putting all the parameters into the u, the v, finding for your magnitude and also your direction, you are going to get these data points. So now we are going to draw these data points or this set of data points on our graph sheets. So let's assume this is my graph. So I have my graph here, and we are going to draw in the upper right quadrant, right? And always remember that you would have to indicate your stagnation points on the graph. It's very necessary. You have to indicate it. So the stagnation point we had was -2/7 for the x. So let's send it to our decimal. We are going to get, that's -0.286, and also -0.14. So let's leave this to 2 decimal places. So this is our stagnation points. So we are going to get the scale for our graph, and we are going to plot y against x. So y on the y direction, or on the y axis, sorry, and x on the x axis. So we are going to generate our scale. So let's say 1, 2, 3. Same applies to this 1, 2, and 3. So our first point is 1, 1. So let's say the 1, 1 is at this side, and the magnitude is to get the distance of the particle, the length of the particle, and the direction, that's the tan inverse of v over u, is to get the direction to which the particle will move. So bear in mind that this 7.8, 10.82 are all in meters, but our graph sheets or our graph, it's in centimeters. So you would have to do some scaling there. So you can say 1 centimeter is to 1 meter. So 1 centimeter is to 1 centimeter is to 10 meters. So you can write it here, maybe 1 cm is to 10 meters per second, so that we would know, or 10 meters, so that we will know that, okay, this is the scale you are using to be able to measure the distances of the magnitude and all those stuff. So this will help us draw our stuffs well, the scale. So we start with 1 and the magnitude is 7.8. So if 1 centimeter is to 10 meters, it means you are going to draw 0.7 centimeters. That's 7 millimeters, or almost 8 millimeters. So with direction, they said negative 1.5, negative 50.119. So for the negative 50.19, how will you know that it's in this direction, it's in this direction, it's in this direction? This, our u and our v, would help us know which direction is supposed to be. So we know for our u, we know that is the x-axis, and our v is the y-axis. So for the x-axis, we know that this side is positive, this side is negative. This side, for our y-axis, this side is negative, and this side is what? Positive. So if you look at our data points or our sets, you can see that all the u's are positive. So it means the u will be positive here, and all our v's are negative, and the v is somewhere. So the negative v here and the positive v here, it means the direction would be here. So it will be directed towards this angle. You get it? So this is the angle, or this is the direction in which the data points would be. So it means for the 50.19, you are going to measure. So let's draw this wall. Using your protractor, you measure wall. So from this side, you measure 50. So let's say if this is 50, then you just draw. So you make sure that this distance is 0.78 or approximately 0.8 if for exam purpose. So this side is going to give us 50.19. So that's what you are going to do here. So something like this. Mine is not drawn to scale, so you bear with me. Then the next one, we have 1, 2. So for 1, 2, 2, the same thing, a little bit. Then 1, 3, the same thing. Then we move on to the next point. That's 1, that's 2, 1. So our 2, 1, we have something like this. So they are going to be in this form. So this is how it's going to be. So as I said earlier, you have to draw your stagnation. So the stagnation, so if here is -1, -2, -3, here is -1, -2, -3. We are going to draw a stagnation point, and they said the stagnation, the x is -0.29 or -0.3, which will be somewhere here, and our y is -1.4, which will be somewhere -0.14, sorry, which will be somewhere here. So let's assume, so our stagnation point is somewhere here. So this is how to go about this type of question. Thank you very much for watching this video. I would like you to subscribe, also like, comment and share this video.